Greetings and salutations. Today we're going to have a look at analog meters. Analog meters are still widely used, even though we do have our digital meters. There is certainly a place and a time for using an analog meter, and we'll be looking at that. And we'll be discussing voltmeters and how they work, amp meters, how they work, and how we can reconfigure them to give us readings, dial readings, based on what our needs are, but not necessarily based on what the current dial or the meter is currently set up to provide you. So we're going to have a look at that. But first of all, what I wanted to do here was just show you a few of the meters that I have in my parts box, and to give you an idea of some of the different styles. These are fundamentally your basic, everyday, inexpensive meter you can buy on Amazon. Bought these several years ago. I don't know, $6 to $10. I don't know, maybe they're even $15 now a piece. They work great. They're not super accurate. We'll see how accurate this voltmeter is when we actually go in and start measuring different parameters on this meter. Okay, so this one is 0 to 20 volts. This one is 0 to 50 volts. This is an amp meter, and that's 0 to 50 amps. You cannot put amperage, you cannot put this directly in series with your load. This would become a light bulb very quickly, give you a big puff of smoke, and it could even, if you had enough amperage, like 50 amps, could actually depart from its casing. So please be very careful about that. If you notice on this right here, it says, I'll get it up nice and close if I can, 75 millivolts, and it shows it going across a rectangle, the rectangle being a resistive element shown in European style, or basically any other style other than North America. Let's just say USA, which we use the squiggly lines, the sawtooth type lines, triangle type lines. So let's have a look at case styles. So standard case style, 2 mounting lugs down here. These are your connections, your wire connections here. And this is pretty standard. So you can see these 3 are all from the same manufacturer and same style, an 85C1 style sitting underneath the thing there. So 85C1, you can see that even the amp meter is an 85C1. And we have a couple other styles. This is a similar looking meter, DC microamp meters to 50 microamps. It has mounting studs diagonal to each other. They just haven't bothered putting in the other 2 mounting studs on this particular meter. So that mounting style with 4 studs, so this will fit in a 4-stud mounting style, will fit pretty well any other meter with this kind of style, or any other kind of panel opening with this kind of style. So then we have this one. This is a 4-stud. This is an older style meter. This one is milliamperes AC. This is AC milliamperes. What I may do when we're talking about the amp meters is I may take the back off of this one, and we'll have a look inside and see what's going on inside there. Also, the needle is not zeroed, even though our center is zeroed. So there's probably something else going on inside in the movement on this one. This is, so these are standard round hole type mounting scenarios. This is a DC microamp, 0 to 100 microamps, okay, flat panel type. Very, very nice little meter. I have 2 or 3 of these. yeah, so that a little different again. Now in this particular case, when you're mounting these, they have the mounting holes here. They also have mounting studs inside here. So you can either do a through hole type, or you can do this pre-threaded stud type here. So your mounting is going to be a little different. Probably have to do it on standoffs or something like that through your front panel. And then we have this really big guy here. This is AC amperes. It goes up to 200 amps. Now, you can't put 200 amps through this. Normally, amp meters are in series or they're across a load. In this particular case, they're across a load. Right here it says, caution, use only with an external transformer. And the reason being is they're going to take a lot of power, a lot of current, and they're going to reduce it down and apply it to this meter. Now, I went and looked this meter up, and I have the model number, etc. here. It's a 1359. Simpson, by the way, has been in business for many, many years, as long as I can remember, and I'm old. And they produce all kinds of test equipment still today, and all kinds of meters that are used everywhere today. This meter is still sold by Simpson. I don't know how long I've had this meter, most likely a very long time. So the impedance of the coil is 0.008 ohms, and that's very important. The specification for this meter is, in fact, DC current up to 5 amps. So if you provide 5 amps into this meter, you will get a full deflection. So that tells me that the transformer that's bringing the power down to this meter is going to go from 0 to 5 amps. And I'm not sure what the actual configuration is in here, if it's got a rectifier in it or not, a bridge rectifier in it or not, or if it has to go across a load. My thinking at the moment, with an 8 milliohm impedance of coil, yeah, it's going to have to probably go across a shunt, or the rectifier is internal and it's already taken care of it. So just letting you know. So in other words, it's basically a voltmeter that you can pass up to 5 amps into it. Also, the internal configuration of this meter is different than the internal configuration of any of these other meters here. This is what they call an iron core meter, and it actually is like a solenoid. Instead of having a wire wrapped around the meter movement, as in these ones, and then you apply power into that meter movement, which is gimbaled around a permanent magnet, which then, of course, the more current, the more the meter dial will move. In this one, it's a solenoid, so it's actually 2 iron pieces, and the needle movement is attached to one piece of iron that is gimbaled, and then there's a fixed piece of iron around that, and then there's a coil of wire around that fixed one. And we're passing the current through a coil of wire, just like on a solenoid. So it's a different type of meter movement operation, and that's one of the reasons why you can pass a lot of current through this meter, 5 amps, because that coil of wire, you can just wind that, use the gauge of wire larger and larger to handle the larger currents. Obviously, there's a point of no return where the wire gauge would be too big to actually fit in the meter movement. So anyway, just wanted to point that out. This is a little bit different. All right, so that's kind of the overall. Let me show you this meter. This is for a project I'm doing right now for a signal generator, a complete rebuild of a signal, well, not a complete rebuild. rebuild of a reconstitution of a signal generator. And this is the meter out of that particular piece. This one also measures microvolts, and then it comes out of a tube or valve piece of equipment, and it works in very low milliamps anyway. But yeah, so this is just another mounting style. This particular one has 3 holes, and this particular mount style is, let me see if I can see where I have that. And you know what? I do not see the model number on here, or the mount style number, and I can't remember it off the top of my head. A W something. Anyway, yeah, so that's just a little bit different mounting style. All right, so the first thing we're going to do is we're going to look at voltmeters. Now, there's a lot more about voltmeters than you may know, and certainly for the up-and-coming folks that are interested in electronics and are going to possibly want to purchase some of these in the secondhand market, eBay, etc., and you don't know what you're getting. There's no markings on it. You don't have a model number, etc. Can't find any information. We're going to go over how we can figure out what's all going on inside, and then we're going to figure out how we can change the scaling on the voltmeter. We are going to do the same thing with amp meters. So remember, amp meters are also, they are voltmeters. Okay. All right. Let me get this moved out of the way. I'll get set up for looking at voltmeters, and I will be back in a moment. I have the voltmeter here, moved all the other meters out of the way, so we're going to have a look at this guy. And first thing we're going to do is we're going to apply voltage into this, up to 20 volts, and see how accurate the meter movement is. Let me just check real quick here. So the zeroing on the needle here is pretty good. I don't know if you can see that. The parallel, you can focus for me. There we go. So you can see it's pretty well dead on. So we'll see how accurate the meter is at this particular moment. And then if it's not accurate, we will go in and see about making it more accurate. And then we'll talk about how we can change what the value is shown on the needle or on the face of the meter relative to what we want to change it to. So let me hook up negative. I'm just going to make sure I got negative. So just be very, very careful when you're doing work with these meters. This meter, and you really actually cannot see that, but the negative of this meter is right here. You can just barely see it by my thumbnail. The positive side is not marked. So a lot of times, the positive side is marked and not the negative side. So just being the person that I am and not wanting to make a mistake, I will mark this as negative. If I can just put it right on top of the same one, that can go negative. I guess my Sharpie here is kind of running out. There we go. Got a little negative on there. I don't have a red Sharpie, otherwise I'd put a red on that side. So just be careful. If you hook these up backwards and pump 20 volts into it, just all of a sudden, for instance, the needle will travel up so fast that it'll have a lot of energy behind it, and it will hit the stops on the inside, and you could possibly bend the needle. So one of the things you don't want to do is pretty well specify a meter that reads full scale when you first turn the power on, and the power just comes on suddenly. After a while, that meter movement's going to get probably out of whack. And one of the other things you don't want to do is damage the hairsprings inside. You damage the hairsprings inside, the meter's pretty well shot. You don't, and again, you don't want to hook it up backwards because then the needle will deflect in this direction, and it could deflect very quickly, very hard, and damage the movement. So just a quick thought about that. Just checking to see that I've got the positive on the correct side, negative on this side. Make sure I can put it out here into view of the camera. And let me just zoom this in nice and close, and I will look at my power supply. I have it all at 0 right now. By the way, this Siglent power supply is actually quite accurate in voltage output. It does only go to 2 decimal places, both in voltage and current, but it is actually quite accurate. I've tested it with my DVM, which is also very accurate. Anyway, so I just wanted to point that out. So I am channel 2. I'll turn channel 2 on. I'm at 0 volts. I'm going to raise this up to 20 volts, thusly. So you can see that the meter is about 1 division, or 1 little division, half division, out. So it's not scaling correctly. What generally causes this problem in a voltmeter is the series resistor inside. So let me turn this down and off, and I'm going to just very quickly draw what we have here. Now this is really for our new friends just becoming involved in electronics. So let me zoom out here a little. So the inside of the meter is like this. We have basically 2 resistors. And I'm drawing the resistors European style because that's just the way I like to do it. And this is negative side, this is positive side of the meter, and this is the meter. This is the meter coil, and it has resistance, okay? And this is going to be the series resistor inside. The coil is a fixed value. We can't change the value of the coil, and its resistance is going to be quite low. So, but what we can do is we can change the series resistor, and that's internal here. So then, how do we start to find some values here? Well, first of all, we're putting 20 volts across here. So if we have 20 volts across here, what would be the next thing to do? We don't know what the meter coil resistance is. We don't know what the series resistance is. We're going to find this out, of course. We're going to calculate those. So what we need to do is we need to measure the total current coming through this series system here. So let me quickly take this off of here, and I'm going to take my meter, my multimeter, and I'm going to hook it up in series. It is already set to read amps. It's actually all the way down to microamps. So it's right now these leads are acting like antennas in the microamp range. And that's a whole another subject when it comes to electromagnetic fields and transmitting radio waves and all that kind of fun stuff. So we're going to hook that up in series here. So the meter is now in series. Current's going to come in. It's going to go here. It's going to go up to the meter, through the meter, back down to this meter, to the digital voltmeter. And I'm going to measure the current coming through. And we're going to write that down. So let me bring this up to 20 volts. Thusly, 1.128 milliamps flowing through the meter. There'll be a slight drop because of the resistance of the wires, but I do have those zeroed out. So it should be, that would be in the micro um, ohm range. So we're just going to ignore it. But at this moment, what we have is we have, for a current flowing through here, we have 0.00111286 amps. So you can see, if we put a comma right here, it's 1.1286 milliamps. Okay, so now that we have this, this is a fundamental Ohm's law. We take the voltage and we divide it by the current, and we're going to get the resistance. We're going to get the total resistance, meter coil, and the series resistor. Now, we know that the meter coil resistance is very small. So it is fundamentally washed out by the size of this resistor here. And but that really kind of depends on how many volts the meter is actually reading. But 20 volts divided by 0.001128 is 17,721. So the resistance is 17,000. Whoops, I should actually put it over here. 17,721 ohms. And that's the total resistance. Total R. And I'm going to grab my eraser here. Well, probably that's not going to make any difference. Just leave the 17 there, because the resistance of the coil is so low that I'm still going to be in the 17K range here. Okay, so where do we go from here? Well, we still can't figure out what the coil's resistance is, and we can't nail down exactly what this resistor is, because they're in series, they're adding up, and they're adding up to this. So the next thing what we're going to do is we're going to open the meter up, take the back off the meter, and we're going to have a look and at the series resistor that's in there, and we're going to measure that series resistor. And in all probability, as I mentioned earlier, that series resistor is probably not the correct value, and that's why we're getting, it's a little high. I can already tell you right now, the value of the resistor is a little bit high, probably a few hundred ohms maybe, and it's causing the meter to read a little bit low. All right, so hang on a half a sec, and I will turn this meter around, and we'll take the back off and have a look at it. Please stand by. Okay, so I've grabbed my Phillips screwdriver and taken the leads off the meter. Let me just bring this in a little bit closer for us, and make sure we can see what we want to see here. So to take this particular meter apart, all we need to do is remove the two small Phillips screws here. It's kind of nice about these little meters. We don't have to do anything about the front, other than if you're going to do the faceplate on this. There's two little screws here that come off, faceplate comes out. There's two little screws inside, faceplate comes out, and you can put your new faceplate in. So anyway, let's put this down, and we'll remove those two screws, and we'll see what is going on inside this meter. I don't want to lose those two little guys, so we'll just be careful with those. Put them over there. Okay, so that's good. So let's see what we have here. Okay. So not the best in the world. Let me bring this up nice and close to you, and let me see if I can, so you can see, let's see if I can get that to focus and not on my fingers. Perhaps not. Anyway, so you can see the coil of wire down inside. If I move it, you can see it moving, and you can see the resistor that is in series with the coil of the meter. That resistor is coming off the positive side. So first of all, let's just look at that resistor. Normally the resistor when it's blue is a 1% resistor. I'm going to take my eye loop here and have a very close look at the bands. And the bands, there's 5 bands, so that's pretty well telling me it's a 1 ohm or a 1% resistor. And it is brown, gray, black, red. So brown, gray, black, red. Brown, gray, black, red is 18000, and it has a brown bar on the end, which is 1%. So this resistor is supposed to be 18,000 ohms, 1%, plus or minus 1%. Won't bother working that out. You can work that out. It's a couple of hundred ohms. So that out of the way. And if that was the case, this would be a little high. So let's measure that resistance. We will get this sorted out here. Let me just turn that off, and we're going to move my meter from, trying to not put my arm in the way, my meter back up to volt, ohms, etc. from current, and we want to put this in ohms, and we want to zero out the leads. So you can do this on your digital handheld meters also. For instance, I just want to show you. I'm not going to show you how to zero it out, but these guys, your regular everyday DVMs. You can zero. They'll have a provision for you to zero out your leads. If you don't zero out your leads, for instance, these leads is about 35 milliohms, and if you don't zero out your leads, then you have to write that down and subtract that from whatever you're going to read on your resistance when you measure your resistance. But I can just press my little button here. It goes to 0, and we're good to go. So I'm going to put that on there and very carefully clip onto the other side here. Oops. Let me see if I can lift that up just a hair. There we go. And we'll put the lead right on there. All right. So what I'm seeing on the meter is 17,554.3 ohms. So that resistor is in fact 17,554, plus or minus a digit down in here. Okay. So interesting that this is a 1% resistor, but it's giving us this resistance. Now, in all probability, because the needed resistor to drop the current to get the meter to read correctly at 20 volts with that amount of current flowing through it, they probably have to go into what they call the C, D, and E bins to get a resistor or a resistor value that is 1%, that has the resistance value low enough to actually use in the meter. If you're not familiar with component binning, I would suggest that you look that up on YouTube. I won't explain it here because this video is already going to be quite long. Okay, so that's what we actually have for resistance. So now if we take this total resistance and we subtract this resistance, guess what we have? We have the meter coil resistance. So let me do that quite quick, just a little quickly here. And we have 17,721, and we're going to subtract 17,554. 4.4. And we come up with 166.6. So at the moment, and we're going to be double checking this, at the moment, this is looking like 166.6 ohms of meter movement resistance. Okay, so these do come into play later if you're going to use this meter, let's say as a current meter, or you're changing the voltages, especially the series resistor. So if we're taking that information and we're slightly low, then we need to find a compensation resistor, either that we can put in parallel with this resistor, or we change this resistor out completely with a new resistor value that will actually give us the correct amount of current flowing through here. So how we can do that is, we know we're getting this current, total current through the system. And we know we have this resistor, this particular resistance. So now if we want to, we can go like this, and we can take 166.6 ohms and multiply 0.0011286, and we're going to get 0.188 volts. Okay, so that we're getting across here as a voltage drop, we're getting currently 0.1886 volts. So if that's correct, and we have this current, so we know we need at least that. However, this is the part where we have to start looking at this discrepancy, and we have to find out what value we need of this guy. So this currently is what we have for a system here. And it's reading a little low, which means we need a little bit more current to flow, which means we need a little bit lower resistor here. And which then means we have a total current flow that's going to rise. So how do we get that? Well, what we can do is we can take our power supply. I'm going to put my DVM up to volts again, and we're going to hook our power supply back up. Thusly, so let me turn this on. We're going to bring this up to 20 volts, and we're going to see what the meter is reading, and it should be reading what it was before, about one segment too far down. So let's bring this up. So that's 21 volts, and it's a little bit high. So let me bring my control over to the hundredths of volts, and we'll bring this up in hundreds of volts until we reach the meter being in line with 20 volts. Okay. Bring that down a little closer. There we go. So we're now reading 20.6 volts on the power supply, and I'm going to double check that by reading volts here. And that is, as soon as I decide to make a good connection, 20.6026. So 20.6. So you can see that the power supply is producing very close. What it's telling me on its display is pretty well dead on. And we know that we have 20.6 volts for full scale deflection, in other words, 20 volts on the meter. We want to subtract what the meter is supposed to be to what we're actually feeding it in volts, and we get 0.6 volts. So from there, we have to say to ourselves, 0.6 volts with this current through the system, what is that resistance going to be if we want to bring that down? So we take 0.6 divided by Ohm's law again, current 0.0011286, and we're going to get a resistance which equals 531 ohms. Let's say 531.6, and that's rounded to 1 decimal place. That is not finished. This is, again, the total based on 0.6 volts and the total current going through. So we have to remove the resistance of the meter coil from this. So we're going to take that answer and we're going to subtract 166.6 ohms, which gives us 365 ohms. So that's going to be 365 ohms. And it's 0, 0, so we're not going to worry about any other decimal places. So given this, we can now say, basically, if we take 17,554, so we're going to take 17,554.4, which is our measured resistance, and we're going to subtract 365 ohms from that. Subtract answer, and we come up with 17,189. So 17,189 ohms. Let's say 0.4, but it doesn't really matter. The value is so high that it washes out. Okay, so this is what we need in the way of a series resistance value, this one here, to get the correct meter reading. However, 17K is not a standard value for 1% resistors. It's not a standard value for 5% resistors. And let me show you. Will this give this to me? Yes. So if you see here, these are 5% resistors, and we need 17,000 ohms. Notice it doesn't go 17. There's no 17 in between here. This is on 5%, standard sequencing. So let me bring down 1 ohm resistors. Camera's not focusing. Come on, there you go. So these are 1% with a, I think, no, these are all 1%. 17K. So again, the line here unfortunately is in the way. But again, you can see 15, 18. No 17 in the middle. So then you go, oh, well, we've got a dilemma. Well, not really. What we can do is we can do a little bit of parallel resistance, and we can knock this value down to this value in a parallel circuit. For you beginners, this is where your series and parallel circuit knowledge comes in. So 2 resistors, R and R. Let's say this is R1, this is R2, and we are looking for R total. Okay, so we know R1 is 1,755.4. We do not know what R2 is going to be, but we do know what RT is going to be. RT is this guy. So For you folks that are just beginning, for parallel resistors, you've probably already done the calculations for parallel two resistors and two or more resistors in parallel. However, we're dealing with just two resistors in parallel, so we're just going to do the R1 times R2 over R1 plus R2 division. However, we need to find RT. So that, to find RT, it's actually really simple. Instead of adding the two resistors together, we're going to subtract RT from R1. So that is going to look like this. It's going to be R1 times RT divided by R1 plus RT. Oh, sorry, here I am. Already, that's just a habit. That's just habitual, that just going plus automatic. RT, sorry about that. So, and then this is going to equal R2, what we need for a parallel resistor. Okay, so let's figure that out. Let's take the calculator here, and we're going to take 17554.4, and we're going to multiply 17189.4, and we're going to make that equal, so it gives me that, and then we're going to divide that, but now I'm going to use brackets and do 17554 minus 17189.4, 17189.4. That 0.4 is going to disappear kind of nicely. Give us a bracket and hit equal. And so for R2 to be in parallel and bring that down to where we need it to be, that resistor value is going to be 826,711 ohms. Okay, that's the parallel to give us a total needed ohms of 17,189. So let me see if I can find a resistor that might come close to that. I will be back after I dig through my box of goodies here. I dug through my resistors and I have some 1%, and what's really nice is we have 820K. We do need 826K, but 820 is probably good enough because there's a swamping factor that happens, and I just dug a resistor out. I haven't measured these to see where I'm gonna go with it. Let me see if I can put this meter up on my hand, because I have to put the resistor in parallel with that resistor down there. So let me see if I can bring this in a little closer. Now you can see that the meter still is reading off. It has changed a little bit, and that's probably because things are warming up, like that coil, but let me see that. Okay, there we go. So that's what the resistor in parallel with the other resistor brings it right up to the 20 volt mark. So a quick way of adjusting your meter. This one isn't out really all that far, and in general, I mean, if you're out 0.6 of a volt for 20 volts, that's really nothing. If you need much more accuracy than that, then you have to go to a digital meter. And of course, if we were measuring 0 to 1 volt, for instance, then that discrepancy is going to, or that meter discrepancy is going to matter quite a bit more. So that's when you might want to either put a resistor in parallel with it, or which what I have done in the past. I just happen to have one sitting right there, top of the power supply. I have literally mounted little trim pots inside. This is a 20-turn trim pot, and I have literally mounted little tiny trim pots inside. And then if you've got enough room, you have to have enough room. This one would actually have enough room to lay this down sideways here and then put a little hole through the top or the bottom, and you'd be able to adjust this. And then just, kind of touch it, glue it in place so it can't move around. So now you could dial that meter in pretty well exact. But that would be on meters like when you're dealing with microvolts or millivolts, where you need a little bit higher accuracy. Generally, those meters are going to be pretty accurate anyway. Okay, so I wanted to show you all of that. Okay, I wanted to just recap quickly on everything that I've touched in more detail earlier and wrap this all up into a nice, neat little end segment here. What I've got set up is a resistor that is going to replace this resistor. So I have power coming in through the resistor, and then this pin clip is actually jumpering across. It's jumpering this resistor out. So I'm going straight through the meter back to the power supply. I've calculated this resistor to give me a full scale reading of 2 volts instead of 20 volts. So that is a multiplier of 10. So it's a decade lower, okay? Just for convenience. You could do this with 1 volt, you could do it with a half a volt, it doesn't matter. But in this particular case, we have to replace the resistor internally with this resistor. Okay, so let me show you really quickly before I show the calculation. So we put this up here. I'm going to turn on my power supply, and I'm going to bring this up. There's 1 volt. My power supply is reading 1.1 volts. So you can see that the resistor value isn't quite there, and it's true. I had to literally go in and measure each of the resistors until I found one that was relatively close to the one I wanted. And this is why using a trim pot for these low values is actually really good, because you can just trim out the error. So that's at 1 volt, and we go to 2 volts. So a little bit low on the meter for 2 volts, and I'm reading 2.2 volts on the power supply. So if I went 2.3, it's going to come up. Okay, so we can trim that out, or if you can find a more exacting resistor, that's going to be more difficult. So if you can handle that little tiny bit of error for 2 volts, which is a pretty small percentage, then you wouldn't worry about it at all. Okay, let me turn that back down and turn the output off. Move this out of the way. Let's not try and break anything. There we go. Okay, so to calculate that new resistor, it's basically just a ratio. And what we do is we have 20 volts, and we want 2 volts. So if we have 20 volts and our current resistor is 17754, it's not 17, it's 17554 ohms, okay? 17,554 ohms. What ohms do we need to get 2 volts full scale? Simple ratio. And what we get out of this is, because it's 1 decade lower, this is a really simple calculation. It's going to be 1755.4. Okay, so that's what this new resistor should be if I could get it really accurate. And I can't remember exactly what I measured, but it was, I think it was 178 something. So it's a little tiny bit out. I'm not going to worry about it with this meter for 2 volts full scale. That error was nothing. Okay, so that's how you would calculate a new series resistor, internal series resistor, to get a 2-volt reading on a 20-volt. And of course, you can do that with any meter. For instance, a 50-volt meter, and you wanted to read 5 volts. It's a by 10 scale again. Okay, so of the resistor. So what if we want to read 30 volts full scale instead of 20 volts? Well, that's just adding a series resistor in series with the resistor that's already in the meter, or you can just replace this series resistor with the resistor you calculate. And to do that, it's again, we take the 17554 and we're going to have that at 20 volts. I'm just flipping this around, the equation. It can be on either, this can be on either side, it doesn't matter. And we want 30 volts. So if we have 17K for 20 volts, what do we need X for 30 volts? Again, ratio. So instead of I calculated this out a little bit earlier, just so it makes this a little quicker. And what we want is this calculation comes out to 26,331, 26,331.6, but that's the 0.6 is washed out. If we were going to replace this internal resistor, but let's say we're not going to replace the internal resistor, it's kind of, why would you do that when you can just add a resistor in series outside of the actual meter itself? So if this is the new internal resistor, then what we have to do to get the new external series resistor, we need to subtract the 17554 from this, and we come out with 8,777 ohms. And so what I did is I dug through my resistors. The best ones I could come close with was 9,100 ohms, or 9.1K. And I measured through all of those little resistors in there, and I found the best little guy at the closest value I could find that would fit this. I can't remember what the exact value was, but it was pretty close. I think it's within 66 ohms. Yes, I wrote that down. It's actually within 66 ohms of that. So what we'll do, that's unconnected. We'll disconnect that positive lead. We will take that one out of there. And so, like I was saying, this is going to be in series, external to the meter. So what I'm going to do is now I'm going to change this over, and I'm going to grab onto this resistor on that side, which is the input post side, which will basically simulate me just connecting to there. But we want to put this resistor in parallel with, or in series with this. And now when I am going to just move my fine control up so I don't have to spin this too much. So now we should be able to get this up to 30 volts. There's 30 volts. So you can see it's still just that little tiny bit out. And that's that internal resistor, plus a little bit of error on this one here. So a series resistor in series and 30 volts on the power supply. So now we've just changed this meter to read 30 volts. So I did mention earlier, let me turn this off, run the voltage down, turn that off. I did mention earlier about the software, the Tonne software, and I will put that link in the description. And so, as you may remember earlier, I talked about the Tonne software. They made a software that allows you to redesign the face of a meter to fit what you're changing your resistor values to what you want to change your meter to read. So I'll put that link in the description, as I said. So there we have it. I'm going to cover amp meters in part 2 because this is a very long video. I'll try and keep the amp meter video a little bit shorter, but there we're going to talk about shunts and bridge rectifiers and stuff that could be mounted inside or not mounted inside the meters. And so you have to be a little bit more cautious with amp meters when you're hooking them up. Okay, that's it for now, and I will see you in part 2.